the Tesla ventilator, and well, these things. Let's talk about them. G'day everyone, my name's Chris, and well, today is going to be a very sort of different episode because, well, for those who don't know, I'm actually a nurse by trade, and with more than 20 years experience, particularly in anaesthetics and a little bit in ICU, I thought it would be very worthwhile to look at what Tesla has done in the development so far of getting their own ventilator out there. And also, I want to talk about these things and the significance of them. But first, a very, very quick primer as to how we breathe and what mechanical ventilation is, okay? So, first up, to breathe, basically, you've got a muscle down here called your diaphragm muscle, and you've got your intercostal muscles around your ribs. And what they do is it pulls down your actual lungs, and in doing so, creates a negative pressure within your lung space. And so the air out here has to go only but one way, down into there, okay? And then when you breathe out, the muscle relaxes, and then that creates a bit of positive pressure, and it gets pushed out into the air. This is how we breathe, and we do it typically 12 to 20 times per minute. But when you're talking about mechanical ventilation, what we have to do is take either some air, some oxygen, maybe nitrogen, or maybe some anesthetic gases, but that's more for surgery. And we actually push the air into the patient. So this is called positive pressure ventilation, and it's very, very different to normal breathing, and in doing so it has its own consequences, which I'll probably go into more later, but essentially it's something you don't want to do unless you really, really have to do it. Okay, so this, in Australia, we call these things Air-vivas. In America, I think a different name. Forget what you guys call them. UK, probably different again. But nonetheless, this is used typically by paramedics when they go out to a scene where patients actually either in respiratory arrest or who need CPR, and we also use them in hospitals as an emergency backup. So again, to do some life-saving stuff for a patient, or conversely, if the ventilator or anaesthetic machine should go down, we can actually default to this, and by every single bedside in an intensive care and high dependency area, you've got one of these ready to go. So, very quick design of them is that you've got your piece here that actually normally goes to a face mask, but where we can actually also connect it to a patient. So you typically have a filter between this device, and this is an endotracheal tube that you normally put into a patient's throat and down into the lungs to help them breathe, and you connect it there, and this is the bag. Now the bag is got this sort of, I don't know, it's like a rubber material, and it bounces back. It has a bit of a memory to it, so that when I squeeze the bag, I'm pushing air. Have a listen. I'm pushing air down into the lungs, so that's the positive pressure, and lungs fill up, oxygen and air goes in, and then as the patient expires, the air comes back in through this tube, and there's this very cool, what I call duckbill valve, and I wonder if I can show you that. Let's see if we can do this. It's going to be really hard. There we go. You can kind of see that. Hey, here we go. So you see how it opens and closes? So when the air comes back from the patient, it hits this little V-shaped valve, and then it gets blown off to the sides and escapes around the edges on these little valves here. And this is great. This is very, very primitive, very, very basic way in which you can actually breathe through a patient. Now, the videos I've seen so far actually have these little contractions, and I'll put some video on now, of them squeezing the bag or pushing the bag in some way with an automated device, some sort of motor. This is a 2-litre bag. We typically breathe between 5 to 10 mils per kilogram per breath. So for your average adult, that's about 400 to 500 mils per breath. This is 2,000 mils. So if I do this, I'm going to blow up and destroy my lungs. Yes, and you do not want to do that. You do not want to do that. It's called pneumotrauma, and you can break the alveoli, the little tiny pockets that exchange the air with the blood, and doing so, could mean atelectasis, areas of the lung that can no longer function in the gas exchange, and this is going to be very, very bad for a patient. So we are very, very careful when we're mechanically ventilating a patient to not overinflate. And just a little thing out there for those who are into, advanced life support. Remember, less is best. Okay, so don't overinflate and don't push in too much air. It should only be like a gentle squeeze, just like that. A little squeeze. That's enough air, and that's way too fast for an adult. And yeah, okay. So first things first, don't overinflate this bag. Sorry, don't over push this bag. You're going to actually destroy the lungs and do a lot of damage to the patient. Okay, so for that very reason, these things are only good at what we call intermittent positive pressure ventilation, and that is to say that we deliver a set amount of volume to the patient, and we do that 12 times per minute. So if I did a 500 ml breath, okay, and we did it 12 times per minute, that's going to be 6,000 mils or 6 liters of air per minute, which is a normal exchange that we do quite normally by ourselves. Okay, but that's all these things can do. There's an oxygen inlet that actually takes oxygen from a supply somewhere, be it cylinder, wall, whatever it might be, and that gets mixed in with a little bit of air in here and goes into the patient. In a rescue situation where you're doing CPR, you're cracking this thing to 15 litres per minute, providing hopefully 100% of FiO2, that's a flow of oxygen into a patient, and that's to help keep the brain alive and the heart alive, the primary things to keep us going, okay? But we don't want to run at 100%. You want to actually run as close as possible as like 21%, which is our oxygen in the environment right now. And so if we were to mechanically ventilate a patient for a day using oxygen off a wall or a cylinder, and we dialed it down as low as we possibly can, but remembering this thing works on not only air coming into it, but also a mixture of oxygen. And sure, I could disconnect that and actually just have pure air, room air going in. But that's not ideal because patients with, haven't got very good exchange of oxygen going into the body right now. Okay, so they need a little bit of oxygen, not 100%, but they need oxygen over and above what's in the air. And so we need to plug this in, and we need to be able to control the amount very precisely. We need to be able to control precisely the amount of oxygen going to the patient. And this system doesn't actually help that. In addition, this system doesn't actually have what I would call, what I'm going to say now, PEEP. And PEEP is basically positive and expired pressure. The alveoli for patients with a situation, they like to collapse down, and there's areas of consolidation or pathology within the lungs that doesn't allow the exchange of oxygen into the bloodstream. And so to help facilitate that, we actually put a bit of extra air pressure, constant air pressure to the patient all the time. And this thing, it can't do it. There's no way. Watch this. I'll try and provide constant air supply of air to the patient. Ready? No, that's it. Breath is done. That's all it does. So this is a very, very basic rescue device that you really can't use long term. With that said, I don't discourage anyone from going out there and trying to create one of these things, and that could be a fantastic backup in the situation. Let's say mechanical, purpose-built ventilator should actually break down for some reason. Using one of these for a long time can be very, very hard. And but that said, that's something that ideally you're going to ventilate a patient in ICU for at least 10 to 14 days. This will not cut it. Absolutely won't cut it. Okay, so remember, I'm trying to shoot anyone down here. Anything you can do is great. I promise you. Okay, so let's go to the video and check that out.
Coronavirus. So this is Tesla Engineering. We're in the lab and we've been working on some stuff. We just wanted to share it with you. We're trying to make some ventilators out of some car parts so that we can help out the medical industry without taking away from their supply. So I'm going to give it over to Joe Mardall, and he's going to tell you about what we've been doing.
As Lars said, we've been working on developing our own ventilator design, specifically one that's heavily based on Tesla car parts. We want to use parts that we know really well, we know the reliability of, and we can go really fast, and they're available in volume. So here's our kind of high-level schematic design. You can see that all the red parts here are Tesla vehicle parts, so we've used a lot of those.
Okay, so right there, that's pretty impressive. It looks like essentially there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I reckon a good 2/3 of this ventilator is actually from existing parts that Tesla already has. And well, as you'll see later on, they're using like the screen and the computer that are in the Model 3. And yeah, well done guys, well done.
What is a ventilator? A ventilator is a device that helps patients breathe who can't breathe well for themselves, and it does that by forcing air into their lungs with a pressure or a volume control, and then they exhale passively. And now I'll take you to our first round of prototype that we developed, and Guru can talk you through that on the bench here.
Hi everyone. So I'm going to walk you through the first prototype we've built. So this is the hospital grade supply of air that is going into a mixing chamber, which is a car part that we use.
Okay, so this is fascinating and a very good sort of primer. This chamber here, inside ventilators and anesthetic machines, they have a mixing chamber, and they take in medical air and they take in oxygen, and they can take in nitrogen. And with anesthetic machines, they also have a volatile anesthetic agent that can be like sevoflurane or something like that, and it gets mixed in a chamber. And unlike the Air-viva, just give me a second, that you can only actually set in oxygen or maybe room air by taking off this end piece. Ventilators and anesthetic machines, they actually mix this all together before it gets sent out to the patient. So key important difference there.
In our vehicles, this is where the oxygen and the air mixes together, and then it passes through a valve body, which is used to create the waveforms, the pressure and the volume waveforms. Then the air coming out of this valve body goes to a bunch of sensors. So this is a flow rate sensor, this is a pressure sensor. It then goes through a filter and goes into the patient's lung.
Okay, a lot just happened there, and very important stuff. Essentially, what they're saying was that they've got some pressure monitors, which is very important because you don't want to overinflate or push too much air down into a patient, because that will cause damage to the lungs, the alveoli, and you don't want to be doing that. No, definitely not. You're trying to save the lungs here. And they're talking about also flow sensors, so you need to be able to measure in mils the amount of volume that you actually give to a patient. And kudos to these guys. Interestingly, they've got a filter both here at the patient end, which is actually quite normal, but they also have one protecting at the machine end. And in the Medtronic ventilator that I've seen posted, where Tesla actually purchased some ICU ventilators from Medtronic, that's a mainstream manufacturer of medical equipment. They also have like filters at the machine end and also on the receiving end, and that's very important because you've got to protect your healthcare workers. This is a droplet spread virus, and you don't want to actually be inhaling the same air that a patient is exhaling, because all those bugs and stuff that are sitting in the lungs, they can get out potentially into the air, and by having a filter in place, that's very important. And what I haven't heard so far, and correct me if I'm wrong here, is how they're actually warming this and humidifying it. Two very important things that need to occur. When you thinking about your own, how we breathe, our nose, the turbinates, the structures behind your mouth, going down your trachea into your lungs, are all being warmed. Okay, they're all being warmed by your blood supply, and so as air travels down it gets warmed on the way, and obviously you've got the mucosal layers, and that's sending in a bit of moisture as well. So when we breathe, we actually get warm, humidified air. Okay, and in this case, I haven't heard them talk about those two very important things. Ventilators, particularly ICU ones, they have the ability to actually do that. And if you don't, you're going to be damaged the lungs and dry them out and actually make the work of breathing for the patient that much harder. And you don't want to do that. Okay, let's keep going.
And then carbon dioxide is put into that air and then goes through the exhale pipes and goes through a set of sensors and then goes through the exhale valve, which is used to throttle the pressure of the lungs. So you always keep a positive pressure on the lungs, so which helps the COVID-19 patients to breathe.
Okay, he's kind of saying not quite right there. Essentially, yes, for patients with pneumonia who have got some pathology in the lungs, they're actually not very compliant lungs, and it's very hard to get air and oxygen down into the alveoli where they exchange it with the blood supply. And so what you do is you actually put on what you call end expiry pressure, or PEEP. So positive end expired pressure, PEEP. And yes, you can do that, especially where you've got the pneumonia sitting there and the alveoli just want to collapse. And so you actually keep a constant pressure of air on the tissue, and that will help the exchange of gases, and so therefore oxygen goes into the patient and CO2 comes out of the patient. But ventilators don't need to necessarily do that. You can just literally be putting positive pressure into the patient and let it come out. Okay, but I diverge. Okay, let's keep going.
Their lungs open. So yeah, that's the ventilator first prototype. And now I'm gonna put you over to Ben, who's gonna show you the packaged version of the same.
This system is powered by the Model 3 infotainment system. Up here at the top, we have a Model 3 center display touchscreen. This touchscreen is powered by the Model 3 infotainment computer in here, which controls Model 3 vehicle controllers. These vehicle controllers talk to these precision variable valves. Amazing.
Like, the ingenuity of these engineers is incredible. To think that they've used a car part, a screen, great, a computer, and an infotainment system to actually help potentially patients. Very good job at Tesla. Well done.
On this single piece manifold, which we designed to be easy to put together.
This gives us 3 different ways to control what's happening in the patient. Pressure regulated volume control, pressure control, or volume control for the most amount of flexibility for the most acute patients out there. We also put in...
Wow. Okay. A lot was said just then, and I think it'd be hard for me to break it down. Let's give it a go. Okay. So he talked about different ways in which you can actually ventilate a patient. So remembering, as I said before, when you're doing mechanical ventilation for a patient, it's actually positive pressure. It's quite different to what we normally do. So when our diaphragm drops down, the negative pressure creates and air gets sucked in to kind of keep things in equilibrium. Whereas when you're doing positive pressure ventilation, you're actually pushing air into the lungs. Okay, so first thing you said was pressure control ventilation, and that basically means that you set the amount of pressure that you're going to be inflating at, and the machine then decides as to what the actual volume is going to be, and you can set the respiratory rate for that, and yeah, that's great. What's another mode he said? I think basically basic intermittent positive pressure ventilation, IPPV. And oh, by the way, for my American colleagues, you use different acronyms compared to us as Aussies. So please don't write in the comments that you don't know what you're talking about. We different terms. Okay. Anyway, I diverge. And so with that one, basically, you're dialing in the amount of volume you want to actually be given to a patient. So typically, let's say 500 mils per breath, and you say, I'm going to do 12 breaths per minute. And there you go. You've got 6,000 mils or 6 liters of air being moved into the patient per minute. Very, very simple mode. And that's typically what happens in general anesthesia. And what's the other one? I think he said, basically, PEEP, as I discussed earlier, and that's the positive end expired pressure. And that's keeping a certain amount of centimeters of water of pressure constant within the lung tissue to keep them open and expanded to help the gas exchange so that, patients actually, the cells are kept alive with the life-saving oxygen. So I think that was the 3 he said. And I would say that, well, realistically, there's a lot more they would need to do to make this worthwhile and something really that ICUs would love. And that is, you need to have some sort of spontaneous or synchronization method. So as you're weaning a patient off a ventilator, you actually stop the machine pushing the air, and it waits until it senses that negative pressure created by the patient taking a breath in. And as it does, and when it senses that, it actually then pushes the air into the patient and assists them with their breathing. So there's different modes of that. You can have a mandatory version, you can have a purely spontaneous version, and yes, that would be a very important mode that they need to actually develop before they can get this ready for FDA approval, because doing ventilation on a patient is one thing, that's great, and I think they've ticked those boxes, but you also equally need to have modes that support the patient to actually control their own breathing and to get the physiology back to where it needs to be. So that is to say that when a patient wants to do 20-30 breaths a minute, let's just say, then okay, let them do that, and let's let the machine actually assist them in doing so. The ventilating a patient is not without its risks. You can actually develop and worsen pneumonia on a ventilator. It's quite a common thing that occurs. It's a ventilator-induced pneumonia. And yeah, basically we only want to ventilate a patient if we need to. And it's the absolute last measure you want to do. And the work of breathing, as we wean off the drugs and we allow the patient to actually take over the breathing more and more, that's the thing that we want the physiology to return to normal homeostasis. And as I say, to normal mode. And we trust the body. It does this thing really, really well most of our lifetime, and so we don't want to develop an acidosis where we get too much acid in the blood, so to speak, and we don't want too much alkalosis where the patient is actually signaling the other way, and that's typically when you overventilate somebody. So yeah, nonetheless, don't get me wrong, this is amazing first steps by Tesla here, and remembering that these guys are car makers. All right, let's keep going.
On the bottom, a backup system. So with an O2 tank, our backup battery, and the air compressor, you get 20 to 40 minutes to move that patient where you need to give them the care that they deserve.
Okay, that's great, perfect. Generally speaking, when you actually want to transport a patient in hospital, because typically, let's say you want to send them for an MRI or a CT scan, that's in a different part of the hospital, and it's going to be at least a 10-15 minute journey, particularly in larger hospitals like Royal Melbourne, Alfred, or St. Vincent's. And yeah, you need that battery to do that. But normally you wouldn't actually use a large ventilator like this. There's little ventilators, and we can use those for the journey, and they have battery backup. They can actually just be mechanical devices, which is pretty special. And yeah, okay, perfect though. If the power should go out and our uninterruptible power supply fails, worst case scenario, all hospitals are required in Australia to actually have a battery backup system. It's typically run by a dirty diesel generator. But until that power, should fail, it's good to have a battery backup so you can then actually bail out to, wait for it, an Air-viva. Yeah, last resort. You would actually take this off, plug this onto the, imagine there's a patient filter right here, the little green thing. That's then connected to the patient, and then you actually start doing ventilation for the patient using an Air-viva. Okay, you don't need a machine at all. It does get tiring. It does get very tiring. Your hand gets sore. But nonetheless, this is an absolute last resort. Okay, let's keep going.
Now coming back up to the top, let's see what's happening on the UI. First of all, we've got a respiratory simulator right here. It's basically simulating what a lung does. It has various amounts of compliance and is breathing. That breath is actually being plotted out up here. We have 3 plots for pressure, flow, and volume. And you can see the line moving across as the lung is breathing. Now, if something happens to the lung and constricts it, you can see the pressure waveforms change, overlaid on the history of the previous 12 seconds. That's important so a doctor can see if they're improving or something's going wrong. There's still a lot of work to do, but we're giving it our best effort to make sure we can help some people out there.
Okay, awesome stuff. And might I say that those diagrams look very, very nice, those running charts. That's something that we absolutely use all the time, and not much to say around that really. My only suggestion to Tesla will be to actually make your numbers at the top there a lot larger to be able to see from the end of the bed. Typically when you're nursing a patient and on a ventilator, you'll be down by the foot end of the bed, and the head will be like 2.5 meters away from you, with the actual ventilator sitting right up there. So to be able to, from a distance, be able to eyeball what the actual settings are, so your pressure, your volume, and your rate, and maybe the ratio, or if there's a delay with the actual insertion of air into the patient, or there's a delay set to actually enable the patient a longer time to expire the air that comes out of them. Those sort of things, you need to make them really quite large numbers, and as nurses, particularly like me, with bad eyes, it's good to be able to actually see that from a distance.
Help some people out there.
Okay, so that's that. Now, I hope you've enjoyed this video, and I hope it's been informative. And again, the work that these guys are doing, and in fact anyone in this industrial space, I salute you. Thank you for your efforts, and I'd like to see what comes of this. Knowing now that what Tesla will have to do is get an approval for this ventilator, which in America I believe has to go through the FDA, the Food and Drug Administration. I imagine that there's probably been some temporary legislation put in place to fast track this whole process, because typically the commissioning of a medical device is a long and lengthy process that involves not only demonstration of the machine and what it can do and how it works, but also that there's been studies done around it, and there's patient safety checks that have been ticked off as well. It remains to be seen how fast this comes out, but nonetheless, great first effort. Now, if you've enjoyed this video, please give it a thumbs up and subscribe to me if you want to see more around renewable technology like electric vehicles, battery, solar, wind, and more. And and I do focus on tech. And look, in this day and age, do take care and stay safe out there. And be good, be great.